Hello. This lab will investigate the charges of two pieces of tape and their interactions. So this lab will model line charges of two charged tapes with GlowScript. The two tapes exert a distributed electric force on each other, and so the lab determines the amount of charge needed on each tape for one to float over the other. So, procedure is this. You have two pieces of Scotch tape which are ripped apart, and one has a positive charge and the other has a negative one. One tape is held up by certain objects and the other hovers in the air. This is because the electric force from the other tape, which acts against the top tape, goes against the Earth's gravitational force. By finding the gravitational force, we then can find the electrical force using algebra. And this is because the forces of the electric fields and then the force of gravity are equal and opposite. They both sum up to equal 0. The values of the charge in the electric field are put into GlowScript in order to model the line charges. So, the physics behind all this is Newton's second law, which states that the acceleration of an object produced by a net force is directly proportional to the magnitude of the net force, and inversely proportional to the object's mass. In this system, the forces sum up to equal 0, causing the top tape to be motionless at an acceleration of 0. Newton's third law states that there is an equal and opposite reaction for every action. The two tapes exert equal and opposite forces on each other. They both have the same charge. And so in this model, the value for Q was found using some simple algebra, equating the force of gravity and the electric force. With some algebra, the variable for Q can be singled out, and using the known values, you can derive a value. So the value which is used in this one is 6.154 times 10 to the negative 9. The code essentially initializes the value of the electric field on the top tape due to the bottom at 0, and then it iteratively increases it along the line charges of the bottom tape, going one by one on the line charges on the bottom tape, and then you'll see that the code represents the electric field from all these line charges. The code from the previous lab is used to calculate these electric fields, and so the iteration continues up until the electric force on the top tape due to the bottom tape equals the gravitational force of the top tape in magnitude. Okay, and here's the code. We have our constants put in, the mass, which was 2.15 times 10 to the negative 4 kilograms, the charge, and using this function from the first lab, we're able to discover the value of the E field given a location in another location. And with the rest of the code, the iteration is used. And then with that, here's the model. The force of the electricity from the bottom tape goes up, and then the force of gravity, which is pulling the top tape, is going down. The electric field from the bottom tape is shown by all these lines, each going from each of the charges. And as you can see, the magnitudes are practically equivalent. So, now for some hypotheticals. So what if instead of line charges we just used a point charge? Well, if that were the case, the charge needed for the forces to cancel out would be 7.261 times 10 to the negative coulombs, while the value of the line charges is a smaller number of 6.15 times 10 to the negative 9. So, the question, why do these estimates differ? So which one is closer to the real value? Well, the two estimates make differing assumptions about the physics behind the phenomenon. The point charge has all the charge at the center of the tape, while the line charge evenly distributes the charge over its length. Given that the distribution of the charge is most closer to how the actual phenomenon works in reality, it's likely to assume that the one in this lab is a more accurate value. And so that's it. Thank you.